Okay, let us talk about vibrations. This is a very important topic and is very exciting too. So, has a little bit of calculus and is very useful for mechanical and civil engineering. Let's look at a system that is exposed to forces in time. So, we're not talking about statics anymore. We're talking about a system like a wing, say like an airplane, say um, kind of like an oval shape airplane. This is, well, that is not really good. So let me try again. It's supposed to be a wing. So when the airplane is flying, the air makes the wings vibrate. So if you put sensors on the wings and you measure with time, say a 3 hour period or whatever time you use, and then this is displacement, which is usually lowercase delta. So if you measure the displacement in, could be in millimeters for such a big system, starts from zero, and when the airplane is flying, then you're gonna have displacements based on the frequency of the air, right? So obviously this is in real life and it is not always uniform because you see in the books the displacement is very uniform. The period is constant, but that's usually not the case in real life. But let's begin by understanding the concepts with simple case where the period is constant. So that's where we talk about the spring and the um, mass system. Let me see if I can erase this. So in real life, the airplane will have uneven on non-uniform vibration, but mathematically we can begin by understanding the concept of a spring, because a spring provides that vibration. So if you remember, the spring has usually a lowercase k as a constant, and the units are Newton over meter. So if we work that out, Newton is given by mass and acceleration, so mass times meter, so mass will be in kilograms, I'm sorry, length in meters, and time in seconds squared, divided by meter. So the constant K is really kilograms, which is right here, the mass, over second squared. Okay? All right, and this mass is going to be given in SI, so usually will be kilograms. All right, so the first thing is that when this spring is at equilibrium, the spring is stretched a little bit, but it's not going to move. If you press it, if you pull it, it will move and it will have um, it will have a period. So if you pull it down for a centimeter, I'm gonna post a video for you to watch the experiment. It will go up another centimeter, and that's why the constant is linear. If you pull it too long, if you pull it too much, so that you ruin the spring, then it's not a linear spring. Springs have a linear relationship until the point that you break it. So if you pull it 1 centimeter, will go up 1 centimeter. So the total deformation or the total displacement is 2 centimeters. If you pull it 5 centimeters, it will go up 5 centimeters. The mass will make it take longer or shorter depending on the mass. So if it's longer mass, it will take longer to do the period. So that's why when we talk about springs, a lot of times we see a circle associated with it, because this mechanism of going up and down is, you can associate it with a perimeter of a circle. Why? Let's say, what is the equation for the period? Is 2 pi, well, right there I just told you they're basing it on a circle. times square root of k over m. K is the constant, m is the mass, not the meters, is the mass. Okay, so if we work this again, we will get that k is in units of, this is 2 pi of square root of kilograms over 1, and then k over m. Yes. Or is it m over k? No, it's k over m. Okay, it's k over m. So it's kilograms over second squared divided by, let me check this thing right here, mass, which is kilogram. So actually, I think that I have a mistake here. I'm gonna have to check my notes, but if period is in seconds, then I'm needed. That's why I want to work out my units here, because then it should be m over k, right? Because it will be 2 pi square root of m, which is kilograms, over 1 divided by square root of kilograms per second squared. And then this is 2 pi of square root of kilogram second squared over kilogram, then square root, yeah. So that is the equation actually. So period t is equal to 2 pi second. So 2 pi obviously is going to be a number, so the units are in seconds. Nice. Okay, very well. So what happens here is that if you want the frequency, which is 1 over t, then you're going to have 1 over second. So we're good. So the 2 pi tells you that this is based on the movement of a circle, or the movement around a circle, the perimeter. And remember, the perimeter of a circle is 2 pi. The perimeter of a circle is 2 pi, therefore just telling you how fast is going around the circle. If it's 2 pi per second, is around this a circle that has a radius of unity, so that we have, because remember 2 pi r is the perimeter of a circle, so if this is just 2 pi, r is 1. So this is not a new concept, right? You will see it in different classes, that the acceleration and all these things that have periodic movement or frequency associated with it is function of 2 pi. Because again, we're associated with how long it takes to go around the perimeter of a circle, and it's very easy to know, okay, well, the radius changes by changing the mass, therefore now we're going around a bigger circle. Okay, so this is the first thing. The period is the time that it takes to have a full oscillation. Now, how do we know what is the shape of that oscillation? As I said, with the wing is very non-uniform, but if we want to know what is the shape, then we have to solve an equation. What is that equation? Well, let's say in this case we have a force, which is W, so we're going to say that force W is equal to the force that is mass times acceleration, right? This is m times a, is equal to k and the distance, so kx. All right, so if we say that this is mass times acceleration, which is the same thing as k equal, well, it's equal to kx or minus kx. Actually, this is minus kx because it's going up, right? Or we have to assume a coordinate system. So we're gonna say that is positive. If you say it's positive up, then it's negative f and plus. All right. So when you bring it to the other side, it's plus equal to 0. Perfect. So we have m times a is the mass times the acceleration plus the constant k, which is dependent on the spring, x. And x is a function of time. So we already know that we have a mass times the second derivative of x. That was the first lecture of the year as a function of time, divided by the second derivative. Oh, this is the derivative. So m is second derivative of x with respect to time plus, not divided, plus k x as a function of time. This is equal to 0. Okay, this is is equal to 0 if it's just given the oscillation because of the weight. If you change the weight, you put a new mass, this oscillation is given by the weight. If this is non-zero, then it's a forced oscillation, and usually will be given as a function that has to do with a circle. So in sine, cosine, or it could be an exponential that, exponential of something could be given in terms of sine, cosine because of Euler number. Long story short, if it's different than 0, then it's forced. So this is linear simple oscillation. This is natural oscillation. All right. So if we go, say m x dot dot plus k x equals to 0. If we go to Wolfram alpha, let's see, and we type that, where we divide by m in both sides so that we have k over m here, then we get that the solution to that equation is this guy, which is c1 cosine, c2 sine, and that is what I have one here. So it's sine of k over m as a function of time plus c2 cosine of k over m as a function of time. This right here will give you, which is beautiful, right? Because you can change the spring, you can change the constant k right here. By changing k's, you're changing the spring. You can change the mass, you put a different value for your mass. You find the C1 and C2 as you learned in differential equations with the homogeneous equation. And that basically will give you the shape of the displacement in x. All right. So now remember that this square root of k over m is omega. Okay. This k over m is because we divided this m here, but in the period is m over k because of the units. So they'll get confused. So we're going to have this first equation that I put here. Why is there a second equation? Well, because like in a car, you don't have a system that is just a spring, because usually will be a forced, like a pothole will be a forced oscillation. And then once you have a spring moving, it will take a long time to come back to equilibrium. So that's why most mechanical systems have a damping force, which is a drag force, to keep it from going too crazy on the oscillations. So the first force will make it stretch or will make it compress, but the damping will make it control better on the stretching or the unstretching or the compressing. So this is a little different, because now this here is changing the velocity concept. So this is negative, so because of the convention we're following, it depends is negative or positive, depending if you, a lot of books will take this positive because it's the way of the mass wanting to move, but you just follow your convention. Don't worry about plus or negative yet. You add the plus or the negative depending on your coordinate system. What is important is that there's a damping force. This is only for linear damping mechanisms, which is what we're seeing here, which is a lot of them really. Viscoelastic is different, but we're not talking about viscoelasticity here. This is for like a car would be a linear damping mechanism. And it's in terms of velocity, so x dot. Okay. So the only difference here is that this new system with a spring, a mass, and a damping device will be the same thing. A force is equal to, depending on the sign, say um, positive was going up, so the force going down is given by b dx as a function of time dt plus the same k times x equal 0. Equal to 0 because it's just given that the mass is making the spring move. If it's non-zero, it's because there's a forced, there's something forcing it, like somebody hit it or there's a pothole, etc. There's an external force. So let's do the same thing. Let's bring this to this side, and then it's basically ma is the second derivative of the displacement with respect to time. Okay, plus b dx dt, x as a function of time, plus k and x as a function of time. This is the unknown variable. This can be basically written as, let's divide the m divide everywhere. So x dot dot plus bm x dot plus km x equals to 0. So if we put that in our Wolfram alpha helper, we're gonna have, let's take this guy and edit it. We're gonna have that we're gonna do b divided by m times the first derivative of x with respect to time, and that equation right here is this guy. Okay, so yep. Actually, no, this isn't. This is mapping to a different domain. Is this guy? So differential equation solution. We're not going to change it to a Lagrange domain. We're not going to try to control it or anything. Instead, we're going to keep a differential equation solution, which is this guy. So instead of being cosine and sine, it's an exponential. All right, so that is why I have it down here. So say a is the constant, and you have b time divided to 2m. So this is the b is the coefficient of drag or the damping coefficient, mass, and omega we already know is m over k, and then any initial conditions for your oscillation. If not, this will be just omega t. Actually, a lot of cases, most cases, you don't see this because you're starting from an initial point where there's no initial vibration. So these two things are equivalent. It's just that this is in terms of C1 and C2, whereas this one is exponential and cosine. So you'll have to check what solution is going to work for you, but BT2, if you follow mathematically this and this will get to the same place. So you can choose what route to take. Yes. So depending on what book you use, it will actually tell you, yeah, it's because one is based on the homogeneous solution and one is based on the general solution. So this is for the homogeneous solution, which is equal to 0. And this is for the general solution. So cosine, yeah, both equations will, for the range of time that you're gonna use, both equations will take you to the same points. But since I have an homogeneous solution, I'm going to get rid of this. And I'm going to put this here. Because, yep. All right, this is the solution to that equation. You can just follow Wolfram alpha and you'll get it by yourself. So it's basically exponent. T is the variable. You can just plug in whatever t you want to choose. And this is b squared, which we already mentioned is the damping coefficient, k, m, mass, and spring constant, plus b divided by 2m. So all those are numbers except for t. C1 and C2 are known at the initial conditions. So yeah, let's go ahead with use this equation right here. So if you notice, this one is sine and cosine. This one is exponent that is multiplying the coefficients. All right, so that is basically the introduction to vibrations. In the book is going to be a little more complicated. I just wanted to give you this simple introduction. The book is using a bunch of references to delta, which is nothing more than x. So like this is the same thing as kx, but it's a little annoying because you're wanting to solve for x. So later on they'll have to bring delta back to x, and it's just a little more complicated to follow.